Example 10. Test the convergence of the sequence an is equal to n square upon 2n minus 1 sine 1 upon n. Now in this question, for a given sequence, nth number of term is given, an, okay? And the question is that test the convergence of the sequence. So here we are required to check whether the given sequence is convergent sequence or not. Now let's discuss the solution. Now in this sequence, sine 1 upon n function is given, okay? So that's why here we use one important result. We know that limit x tends to 0, sine x upon x equal to 1. So this one is a one result you already studied in previous standard, okay? We use this result to solve this problem. Now actually no need to evaluate this one, but here for understanding purpose I am giving you the solution of this limit, okay? Now how to get this one value? So here what is given? Limit x tends to 0, sine x upon x is given, okay? Now first put x equal to 0 in numerator and denominator separately, okay? So now put sine 0. So what is the sine 0? Sine 0 is 0. Again put x equal to 0, okay? So x is 0. So here what we get? 0 upon 0 form. So this one is the indeterminate form. So to solve this limit, we use L'Hopital rule. So what is the L'Hopital rule? If we get either 0 upon 0 form or infinity upon infinity form, then what to do? Differentiate numerator and denominator separately, okay? आपको क्या करना है? न्यूमरेटर और डिनोमिनेटर दोनों को सेपरेटली क्या करना है? उसकी डेरिवेटिव निकालनी है. नो नीड टू यूज u अपॉन v रूल, ओके? आपको यहाँ पे u अपॉन v रूल यूज नहीं करना है, okay? So first find the derivative of sin x function. So what is the derivative of sin x function? Cos x. Now what is the derivative of x with respect to x? 1, okay? Now after differentiating numerator and denominator separately, again put the limit, okay? So now apply the limit. So put x equal to 0. So what is the cos 0? Cos 0 is nothing but 1, and 1 upon 1. So what is the answer? Answer is 1, okay? So what we get? Limit x tends to 0, sine x upon x equal to 1, okay? So using L'Hopital rule, you can get this result. The same result is also true for the tan function, okay? So you should remember this as a result. Now here this one is for x, okay? But in our problem what is given? Sine 1 upon n is given, okay? Here x is not given, so that's why here take the assumption. What is the x? Here assume that let x equal to 1 upon n. So but x tends to 0 as per this limit, okay? So x tends to 0 means x is 1 upon n. So 1 upon n is also tends to 0. So what we get? N tends to infinity, okay? So now in this result put x equal to 1 upon n everywhere. So what we get? Limit 1 upon n tends to 0, sine 1 upon n upon 1 upon n tends to 1, okay? So we get this result, okay? Limit 1 upon n tends to 0, sine 1 upon n upon 1 upon n equal to 1, okay? Now next step, what to do? Now what is the an? An is n square upon 2n minus 1 sine 1 upon n, okay? So now first here sine 1 upon n is given. Try to reset this form. What we need? Sine 1 upon n upon 1 upon n, okay? So for this value we can put 1. So that's why now reset this value. So first what to do? Here sine 1 upon n is divided by 1 upon n, okay? So in mathematics we know that if we divide something then we need to multiply it, okay? Because we cannot add any extra term, we cannot multiply any extra term, okay? So here divide by 1 upon n, so that's why multiply by 1 upon n, okay? So here we are just resetting this term. Now here we get this form sine 1 upon n upon 1 upon n, so keep as it is. Here now 1 n is cancel out. here 1n is cancelled out. So what we get? N upon 2n minus 1. Okay. So rearrange this term. So what we get? N upon 2n minus 1, and keep this term as it is, sine 1 upon n upon 1 upon n. Now apply limit. Limit n tends to infinity an is equal to limit n tends to infinity n upon 2n minus 1 and limit n tends to infinity sine 1 upon n upon 1 upon n. Okay. Got it? Now listen. Here n tends to infinity. See what we get? 1 upon n tends to 0 implies n tends to infinity. Okay. So here n tends to infinity is nothing but what? 1 upon n tends to 0. Okay. So now for these we can put value 1 from this result. Okay. So this value is nothing but 1. Now from this take n common. So what we get? N upon 2 n minus 1. Okay. So here n, from denominator take n common. So what we get? 2 minus 1 upon n. Okay. So now n is cancelled out and put the limit n tends to infinity. So this term becomes 0. So what we get? 1 upon 2. Okay. So 1 upon 2 into 1 is equal to 1 upon 2. So what we conclude? Limit n tends to infinity n square 2n minus 1 sine 1 upon n is 1 by 2. Okay. So now limit of this sequence is 1 by 2. That's why the sequence is convergent sequence and it converges to the value 1 by 2 because here we get finite limit. Okay. So that's why the given sequence is convergent sequence. Okay. I hope you all should understand. Example 11. Test the convergence of the sequence tan inverse n. Okay, so here inverse trigonometric function is given in a sequence. The nth number of term of the sequence is what? Tan inverse n. Now how to solve this problem? For this we need the knowledge of domain and range of inverse trigonometric function. Okay. So now here few graphs are given. All these are the graphs of inverse trigonometric function. First one is the graph of sine inverse x, cos inverse x. Then third one is the tan inverse x, cot inverse x, cosec inverse x, and last one is a sec inverse x. Okay. So here graph of inverse trigonometric functions are given. From this graph you can understand what is the domain and range of the inverse trigonometric function. In our question tan inverse function is given, so that's why here we discuss the graph of tan inverse n. Now here observe this graph. This graph is for function tan inverse x. Okay. Now here observe what is the value of x. Here x is vary from 0 to infinity. This is the positive direction. Okay. Here in this direction x is vary from 0 to infinity. Here x is vary from 0 to minus infinity. This is the negative direction. Okay. Now here as we put x from 0 to infinity, what is the value of tan inverse x? So tan inverse x function approaches to this red line. Okay. As we take infinite value, the tan inverse x function approaches very near to this red line but never touch. Okay. So this red line indicate the value pi by 2. So what we conclude from this graph? As x tend to infinity, tan inverse x function approaches to value pi by 2. Okay. Same way as x tends to minus infinity, negative direction, x tends to minus infinity, tan inverse x function approaches to the value what? Minus pi by 2. Okay. So now use this knowledge to solve this question. To test the convergence, consider the limit n tends to infinity tan inverse n. We use the standard result. Okay. From the graph we directly write limit n tends to infinity tan inverse n is equal to pi by 2. Okay. So here we observe that here x is given, here x tends to infinity, so instead of x here what is given, n is given. Okay, so here as x tends to infinity means we understood n tends to infinity. So when n tends to infinity, tan inverse n approaches to value pi by 2. Okay, so from this graph we can conclude that limit n tends to infinity, tan inverse n is equal to what, pi by 2. Okay, since the limit is finite, the sequence is convergent. Okay, so here we get finite value, pi by 2 is nothing but the finite value. So that's why we conclude that the limit is finite, the sequence is convergent sequence, and this sequence converges to the value pi by 2. Okay, so here tan inverse n function is given. In exam, maybe different trigonometric function can be asked. Okay, so here the entire figure is given for the reference. So from this you can understand what is the behavior of sine inverse x, cosec inverse x, and other trigonometric functions. Okay, so you should memorize this figure also. So in exam, if other trigonometric function may be asked, so you can easily solve it. Example 12. Check whether the sequence 1 plus 1 upon n is increasing or decreasing, and find out if it is bounded and convergent or not. So this question contain three sub questions. First of all, we need to check whether the sequence is increasing or not. Second, we need to check the sequence is bounded or not. And third, we need to check whether the sequence is convergent or not. Okay, so this question contain three questions. Okay, now first of all, what is the an? An is given 1 plus 1 upon n. Okay, so this is the nth term of the given sequence. Now first question, check whether the given sequence is increasing or decreasing. So for this purpose we need to check monotonicity of the sequence. Okay, so monotonicity of the sequence, how can we check? As we discussed earlier, when we say that the given sequence is increasing or decreasing, if an plus 1 is greater than or equal to an for all n, then what we can say, the sequence is what, increasing sequence. Okay, and if an plus 1 is less than or equal to an for all n, then what we can say, the given sequence is decreasing sequence. Okay, so either increasing or decreasing sequence is known as monotonic sequence. So that's why here first of all we need to check the behavior of monotonicity. That's why what to do here, in this definition, in these two definitions, we are comparing an plus 1 and an. Okay, so that's why here take first the difference of an plus 1 minus an. Okay, so take an plus 1 minus an. So how to get an plus 1? An plus 1 is nothing but the n plus 1th number of term. Okay, so how to get? So in an term, everywhere n is replaced by what? N plus 1. So we get n plus 1th number of term. Okay, so here an plus 1 is equal to 1 plus 1 upon n plus 1. So right here, what is the n plus 1? 1 plus 1 upon n plus 1 minus an. So an is what? Put as it is, 1 plus 1 upon n. So first take the difference of an plus 1 minus an. Okay, now simplify this. So 1, here open the bracket, so minus 1, so this 1 and this 1 is cancel out. What we get? 1 upon n plus 1 minus 1 upon n. Here minus plus become minus. So we get 1 upon n plus 1 minus 1 upon n. Now take the LCM. So what we get? N minus in bracket n plus 1 upon n plus 1. Okay. Now open the bracket. So n minus 1. Here minus is given. So that's why reverse the sign. N minus 1 upon n plus 1. So n is cancel out. You will get minus 1 upon n plus 1. Okay. Now observe whether this one is positive or negative. Here, okay. Now see here. This n this n is from what natural number n? Okay, what is my n? N is vary from 1 to infinity. Say yes or no. What is n? N is vary from 1 to infinity. So that's why n is what? N is positive number. Okay. So denominator is positive. Now here what is given? In numerator -1 is given. So that's why the entire number was negative. Say yes or no. Denominator is positive and numerator is negative. Okay. So that's why the entire number is what? Negative. So what we get? This value is less than 0. Okay. So that's why what we conclude? An plus 1 minus an is less than 0. Say yes or no from this result. Now shift an this side. Okay. So an plus 1 is less than an for all n. So from definition, see here, an plus 1 less than an. Okay, an plus 1 less than or equal to an. So what we conclude? The sequence is decreasing sequence. Okay, so here conclude that an is monotonically decreasing sequence. Okay. Now next, check whether the sequence is convergent or not. Now to check the convergent, we apply the limit on nth term of the sequence. So limit n tends to infinity an is equal to limit n tends to infinity 1 plus 1 upon n. Okay, now separate the limit. So 1 plus 1 upon infinity. So this becomes 0. This value becomes 0. Okay, so what is the answer? Answer is 1. Okay, so now here we get the finite value 1. So what we conclude? Hence the sequence is convergent and converges to 1. Okay, so this sequence is convergent sequence and it converges to value 1. Now next, check whether the given sequence is bounded or not. For this, recall one result. In previous lecture we already discussed every convergent sequence is bounded sequence. Okay, so here we already derived this sequence is convergent sequence. Okay, so obviously from this result this sequence is bounded sequence. Okay, but now let's check what is the upper bound and lower bound of this sequence. Now put n equal to, for this purpose, put n equal to 1, 2, 3 in this nth number of term and get all the terms of the sequence. Okay, so first put n equal to 1, so you get first term 1 plus 1 upon n. Then put n equal to 2, so second term is 1 plus 1 upon 2. And so on. Third term is 1 plus 1 upon 3. 100 number of term is 1 plus 1 upon 100. This is a 1000 number of term and so on. Okay. Now find the value of this term. So 1 plus 1, first term is 2. Second term is 1.5. Third term is 1.33. Fourth number of term is 1.25. 100 number of term is 1.01. 1000 number of term is 1.0001. Okay, and so on. Now here observe the value of the sequence. Okay, so the value of the first term is 2. The biggest value in this sequence is 2 and no term goes above 2. Okay, so 2 is the upper bound of this sequence. The sequence as we move infinity. Okay, then see here, we notice that sequence start from 2 and then keeps getting smaller. Say yes or no? No terms goes above 2. Okay, here 2, 1.5, 1.33, 1.01, 1.0001. Okay, so as we go further in sequence towards infinity, the number keep decreasing and approaches to 1. So that's why what we conclude, the lower bound of the sequence is what? Here lower bound of the sequence is 1 and upper bound of the sequence is 2. Okay, here maximum value is 2 and as we move towards infinity this pattern approaches to value 1. Okay, but never cross the value 1. Okay, so that's why the lower bound is 1 and upper bound is 2. Okay, so that's why what we conclude, AN is bounded sequence. Also we can say from the limit. Here we already derived that limit n tends to infinity, 1 plus 1 upon n is 1. Okay, so that's why, what does it mean? Limit n tends to infinity an means as we move towards infinity, the value of the sequence approaches to 1 value. Okay, but never exceed the value 1. Okay, so that's why also from this and also from this pattern you can observe that the given sequence is bounded sequence and bounded between 1 and 2. Okay, 1 is the lower bound and 2 is the upper bound. Hence, the given sequence is decreasing sequence, bounded sequence and convergent sequence. Okay, this is the conclusion of this problem.